So in this talk, I will mainly focus on the parameterized inapproximability of K-Clique, and then I will mention its connection to the PIH. Okay. So let's start with K-Clique problem. This is a fundamental problem in computer science. Given a graph G and an integer K, the K-Clique problem asks if G contains a complete subgraph with K vertices. So this problem is NP hard, and under assuming NP is not equal to P, we have no polynomial time algorithm for this problem. An approach to handle this hard problem is to pick a parameter and consider FPT algorithm. Unfortunately, assuming W1 not equal to FPT, there is no f of k times polynomial of n time algorithm for K-Clique. And yeah, another approach to handle this hard problem is to consider approximation algorithm. Yeah. For a C approximation algorithm for K-Clique is it output a clique of size k over c if the graph contains a K-Clique. And to show that a problem has no good approximation algorithm, we also consider its gap version. Okay. So after a long line of work, we know that it is NP hard to approximate K-Clique to a ratio within n to 1 minus epsilon. Yeah. A new research problem has been asked from the parameterized complexity. So for an approximation ratio gamma k, we know that we can, in n to k over gamma time, we can enumerate every subgraph with k over gamma vertex, and this can give us a gamma k approximation ratio. Okay, so a natural question is, can we do better? And so yesterday, Xin told us that assuming gap ETH, we cannot. The answer to this question is no. Yeah. So it is more interesting to prove the hardness of approximation for K-Clique under ETH. We believe that study this problem can lead us to a parameterized version of PCP theorem. And in fact, if we can solve an n to square root of k times lower bound for constant approximating K-Clique, then we can prove PIH. And PIH is considered as the parameterized version of the PCP theorem. It says that there is no FPT algorithm for the to approximate the 2 CSP with k variables to some constants. So let us focus on this open problem. Can we prove that ETH implies K-Clique has no f of k times n to square root of k times constant approximation algorithm? And to prove that K-Clique has no good parameterized approximation algorithm, we need a parameterized gap-producing reduction for K-Clique. So this slide showed a parameterized gap-producing reduction for Clique. So given a graph G and an integer K, this reduction output a new graph G prime and a parameter K prime, such that if G contains a K-Clique, then this graph G prime contains K prime clique. If G does not contain a K-Clique, then this graph G prime contains no K prime over 2, contains no clique of size K prime over 2. And the parameter K prime must depends only on K. Right. Okay, so I will move the gap-producing reduction for K-clique here. In 2021, I gave such a gap-producing reduction for K-clique. And this paper is a kind of proof of concept work. Beta reduction for Clique has been given in the following papers. Yeah. And as you can see, there are two parameters about the gap-producing reduction for K-clique. One is the parameter K prime here, and another is the gap. For the parameter K prime, we want it as small as better. And for the gap, we hope that it is the larger the better. Yeah. And in summary, under different hardness hypothesis, this reduction gave us a different lower bound for approximating K-clique. Okay. So now let's move to the main idea behind the reduction for behind the gap-producing reduction for K-clique. Suppose we have a reduction R for that can create a gap for K-clique. So in the yes case, if G contains a K-clique, then we have a large clique in the graph G prime. Now if we remove just one edge from this clique in G, then in the graph G prime, we should remove so many edges from G prime. So this observation tells us that such a reduction must has this local to global properties, which means that any local change in the input graph can cause global changes in the output graph. So the question is how to construct a reduction with such kind of feature, right? And we can use error correcting code. Know that an error correcting code also have this local to global feature. If we just flit just one bit of the input message for an error correcting code, this will cause a global change in the output message. So now we know that to construct a gap-producing reduction for parameterized K-clique, error correcting code might be useful. Okay. So the question is how to use error correcting code to encode a solution to a K-clique problem. And the answer to this question is easy. We use vectorization and parallel encoding. So first, we treat the vertex set of a graph as vector. Then we do parallel encoding. So what does it mean by parallel encoding? We write down the vector as a row vector. So suppose V1 to V2 to Vk is a solution to the K-clique problem. We write down the vector as column vector. Then we apply the encoding function to every. We write down the vector as a row vector. Then we apply the encoding function to every column vector. So this gives us U1 to UK prime. Right. So this is parallel encoding. So the next question is, now we have U1 to UK prime. how to test if U1 to UK prime encode a solution to K-Clique. We can have more information. Assume that we use Hardness code to encode V1 to VK. And all we need to know about Hardness code is it can decode any linear combination of V1 to VK. So one approach to answer this question is we reduce from K-vector sum instead of K-clique. And in the K-vector sum problem, we are given K set of vectors, V1 to Vk, and a target vector, T. We want to pick one vector from each set such that their sum is equal to the target vector. And this problem is W1 hard. So in the K-vector sum problem, if we have U1 to UK prime, and we can use the property of Hardness code to decode the linear combination of V1 to Vk, right? So we can test if U1 to UK prime encode a solution to K-vector sum. So this is this answers this question. In the paper of Chen Fen, Nuket, and Liu, they solve this question by doing some pre-processing of the vertex set of this graph G, and turn this vertex set into some set of vector with Sidon property. And here, the Sidon set property means that any linear combination of two vectors is unique. Then we can use this property to test if U1 to UK prime encode a solution to K-clique. And in our 2023 paper, we introduced a vector CSP problem, and we prove that this vector CSP problem is W1 hard. Then we reduce from this vector CSP problem. Yeah. So as you can see, the constraint of this vector CSP problem is very similar to the Sidon set property. Yeah. So and the main contribution of our paper is in fact a framework to reduce K-vector K-values vector CSP to the gap clique problem. Okay. So in the rest of this talk, I will briefly introduce the proof of Chen Fen, Hanukit and Liu's paper, and our Fox 2023 paper. Okay. So let's first see the reduction from Chen et al. So they start from a color version of K-clique, and they reduce it to a color version of clique with the vertex set partitioned into F to K part, where F is the finite field. And we assume that the vertex set of G is has this Sidon set property, which means that any linear combination of two vertex from G is unique. Okay. So we assume that the vertex set of G is partitioned into K part, and if G contains a K-clique, then we must pick one vertex from each part, and it forms a K-clique. And the graph G prime, the vertex set of graph G prime is partitioned into F to K part. And each part is corresponding to a vector, is corresponding to a K-dimension vector over the finite field F. And if G contains a K-clique, if V1, V2, V3 is a K-clique in G, then we are expect to pick from VR1, we are expect to pick UR1, which is equal to AV1 plus BV2 plus CV3. Here, R1 is equal to ABC, the vector. Right? So this is the reduction. And okay, we need to define the edge of this graph G prime. And the edge of G prime is defined using non-edge. So instead of telling which two vertices has an edge, we are going to tell you which two vertices has no edge. So first of all, every group of vertex, any two vertex from the same group has no edge. Yeah. Every VRI induces an independent set in the graph G prime. And if two vertices from G prime can decode, if we can decode an edge from two vertices from G prime, then we should not add an edge between these two vertices. For example, here, UR1 is from this group, and UR2 is from this group. And we know that UR2 minus UR1 is equal to V1 plus V2. And because the vertex set of G has this Seidel set property, we can decode V1, V2 from this value, from this vector. And then we can go back to the graph G and check if there is an edge between V1 and V2. And if there's no such edge, then we add a non-edge between UR1 and UR2. Okay, so this is the definition of the reduction. Then we need to prove that if G has a K-clique, then G prime has a clique of size F to K. And this is easy, right? If G has a K-clique with one vertex from each group, then we just pick the corresponding vector URI from each group, right? And these vertex are adjacent in the new graph G prime according to the way we define the edge set. So the hard part is to prove that if G has no K-clique, then G prime has no clique of size K times F to K minus 1. And we pick F, we pick F, the size of F is 2K, so we have a 2 gap for the K-clique. Yeah? Yeah.
So can you just at least tell me the graph construction is a bit lost.
Okay. So
you started with this VG and then
VG.
how are you making this VRI?
Well, VRI.
Yeah.
So each RI is a K-dimension vector. Yeah. So this G prime, the vertex set of this G prime is partitioned into this group. Yeah. And each group is contains all the vector of dimension D, yeah, over F. And
so like, what is the rule of this RI? You choose this RI as a vector in F to the power K, correct?
this Ri is f to
is a
power
vector
k.
in f to the power k, correct?
Yeah, yes.
So what is the role? So if you look at the group VRI,
Yeah.
it is just a copy of f to the power d.
F to power, yes. Yeah. It contains all the vector of d dimension vector. So the intuition is if we pick V1, V2 to V3 here, then we should pick UR1 equals to the combination of V1, V2, and V3 with respect to the vector R1. Thank you. Yeah. Okay. Okay. So we are going to prove the soundness part. And suppose G prime has a clique, capital K. Suppose capital K induce a clique in G prime. And we defined a set of R, which we call a good index set R. Index R is good if the clique contains a vertex from the group VR. So basically, the size of R is equal to the size of capital R is equal to the size of capital K, the clique. So we want to prove that the size of capital R is upper bounded by this value. And we have this claim: for every index R that is good index, there exists a direction that every index in this direction is a bad index. Well, in this case, we say that R is conflict with the index in this direction. So how to prove this? Okay. So we have VR here. If we pick some vertex UR here in the capital K, and maybe I should start with just the index R. If we have index R here, okay. So here is the index R plus E1, R plus E2, R plus EK. So E1 means that is a vector with 1 in the first entry. Okay. If so, by the Seidel set of the Seidel set property, we know that using UR. Okay, I should using the linear combination of these two vectors, we can decode V1. Using these two vectors, we can decode V2. And using these two vectors, we can decode VK. Yeah, because UR plus E1 minus UR is equal to V1, right? According to the definition. Yeah. Then, if this index R, if the clique capital K has contains vertex from this index, then we know that in this case G G has no K-clique, right? So now we have K vertices from G. There must be exist two vertices such that they has no edge in the graph G. Now using this these two index, we can decode V1. We can decode V1 minus V2, right? The linear combination of V1 and V2. And then we use the Seidel-Sack property to check that whether V1 and V2 is an edge in the graph G. Okay. So let's assume that we have this claim. Every index R is conflicts with there exists a direction such that R conflicts with all the index in that direction. Okay. So the second claim is for every bad index, it can conflict with at most K elements in the good index. So this is this claim 2 is proved using pigeonhole principle. If we have a bad index not in R, so this index is suppose it conflicts with more than K index. If it contains more than K plus 1 to R K plus 1, then by the pigeonhole principle, there exists a direction I in K such that R1 is equal to R prime is equal to R plus E. Maybe okay. E I here, and it's also equal to. Let's assume that they. Yeah. AB is not is a non-zero element in the finite field. So if there is a bad index which conflicts with K plus 1 good index, then there exists a direction K such that this bad index is equal to R some good index plus A times EI and R2 plus B times BI. Then from this, we can get R1 is equal to R2 plus B minus A EI, right? Then we obtain a contradiction because this means that R1 conflict with R2, and they are both good index. So something must be wrong. Okay, so if you cannot follow the detail, we can just assume that we have this claim 2. Each R prime is conflict with at most K elements in R. Then using this claim 1 and claim 2 and some double counting technique, we can show that the size of capital R is upper bounded by this. Yeah. So this is the reduction from Chen et al.'s paper. It's very simple. So In the next, in the remaining of this talk, I will introduce the framework about reduction. In our reduction, we first reduce K-Clique to some vector CSP problem, and then we reduce this vector CSP problem to the get version of K-Clique. And the first step is easy. It's done by randomly projection the vector from VG to the vector space with dimension D. Basically, we just replace every vertex of VG by some set vertex set with Sidon set properties. So our main contribution in this paper is the second reduction, which we shows that if we have parallelly locally testable and decodable code, then we can reduce vector CSP to the gap K-Clique problem. So what is parallelly locally testable and decodable code? It is an error-correcting code, and it is locally testable, which means that given U1 to UK prime, by querying constant number of vectors from U1 to UK prime, we can test if they're close to a coward of V1 to VK under this error-correcting code function. And it is locally decodable, which means that by querying only two vectors from U1 to UK prime, we can decode VI and the linear combination of VI plus and VJ if U1 to UK prime is close to some coward of V1 to VK. And we also assume that the query of locally test and decode is smooth, which means that every UI is queried with the same probability. And one example of this parallel locally testable and decodable code is the Hardness code. It's our old friend Hardness code. Then with this parallel locally testable and decodable code, we can construct a reduction. So it seems very similar to the threshold graph composition technique we introduced yesterday. In this case, we combined a PLTDC with the vector CSP instance. Yeah. And so here we have this PLTDC. The yellow part is the testing query, and the blue part is the decoding query. We construct an instance of getClique such that the vertex set of this graph is partitioned into T group, where T is the number of locally testing query. So each group represents a query of locally testing. And each vertex in this group is an assignment set by the testing query. And again, we define this graph by non-edge. If two assignments fail the consistency check, then we add a non-edge. For example, every two vertices in the same group fail the consistency check, right? So we should add non-edge here, which means that every group is an induce an independent set in the graph. So another type of non-edge is if two vertices that the the decoding result of two vertices violate the vector CSP constraint, then we add non-edge. So that's it. That's our reduction. And I will not go into the detail of the proof. Yeah. So it remains to construct a good PLTDC code. And Hardness code is a PLTDC. It gives us a reduction with these parameters. And using our framework, we can get n to log k lower bound for constant approximating k-clique under ETH. And another example of PLTDC is derivative code. It can give us a parameter. It can give us a reduction with this parameter, and under ETH we can obtain this kind of lower bounds. Okay, yeah. So now we come to the conclusion part. So in this talk, we shows that if we can have n to square root of k lower bound for constant approximating k-clique, then we can get PIH. So this is still an open problem. And using our framework of vector CSP, we can get such kind of lower bound under ETH. Right? And as I mentioned, I studied the parameterized inapproximability of k-clique can bring us closer to the parameterized version of PCP theorem. Indeed, to prove the hardness of approximating k-clique, we introduced the vector CSP problem and the vectorization technique. We found that if we introduce a vector CSP with some nice property of this constraint, then we can use this vector CSP, the hardness of this vector CSP to prove PIH under ETH. So the differences between this vector CSP and the vector CSP we use to prove our hardness approximating of k-clique is here the constraint of this vector CSP are black box constraint, which means that we do not know any information about this set, and which means that we don't know how to decompose this constraint into some local constraint, right? But if we have more information about this constraint, for example, if the constraints are parallel or linear, then we can use this property to design a PCP for the vector CSP and prove ETH implies PIH. And finally, let me say a few more words about our reduction form to prove ETH implies PIH. In this proof, we actually give a PCP, a parameterized PCP for the 3-set problem. Recall that in a classical PCP, the PCP verifier can only query constant number of bits from the proof, right? So in a parameterized PCP, the PCP verifier can query constant number of lines from the proof. And the number of lines in the proof is bounded by some function of k. And each line contains at most n over k bits. And this such kind of parameterized PCP cannot be obtained by just applying the classical PCP theorem and divide the proof into k lines. Because the classical PCP theorem has this polylog n brought up of the proof length. So in our proof, we figure out how to remove this polylog n factor. So in fact, we did not remove it. We just transform this polylog n factor to the polylog k factor. And so Yi-Chan will talk about the detail of the proof tomorrow. Yeah. Okay, thank you for. Yeah. Questions?
Everyone wants lunch. Okay, let's thank Bingkai again.